We're going to take a look at Bell inequalities from what I hope is a different point of view than one you've seen before. The basic setup is the following. We have Alice, and she has some kind of a system. If we're talking quantum mechanics, it might be a qubit. If it's classical, it could be something else. She's going to measure either A0 or A1. Bob has a system, and he is going to measure either B0 or B1. And each of these can take one of two values, 0 or 1. So when I measure A0, I can get 0 or 1. If I measure A1, I can also get 0 or 1. If I measure B0, I can get 0 or 1. And B1, I can get 0 or 1. Now, what Alice and Bob are going to be doing is they're going to be measuring these things, and they're going to be calculating certain probabilities. The probabilities they're going to be calculating are going to look like this. We're going to have the probability that AJ equals M and BK equals N, where J, K, and M are either 0 or 1. Okay, so each of those things can be either 0 or 1. So these are the probabilities that Alice and Bob are going to get by doing these measurements many, many times. Now let's take a look at these probabilities. There are 16 of them, and each value of J and K describes a particular experiment. And what I mean by that is Alice will be measuring AJ, Bob will be measuring AK. Sometimes they'll get 1, sometimes they'll get 0. They'll use their results to calculate the probabilities. For a fixed J and K, all those probabilities should add up to 1, because that completely describes that particular experiment. But J and K now are ranging over 0 and 1. So that means that this actually the set of all 16 probabilities describes 4 different experiments, one experiment for each value of J and K. Now we're going to calculate these probabilities in 2 different ways. We're going to calculate it using from a local hidden variable theory, and we're going to also calculate them from quantum mechanics. You remember, local hidden variables is an alternate description of reality that says that there's these quantities actually have values before we measure them, and we just don't know what they are. And what Bell's theorem allows you to show is that if you make that assumption, then there are going to be restrictions on these probabilities that quantum mechanics doesn't obey. And in particular, local hidden variables implies that there is a joint distribution for all 4 of these variables. So local hidden variables and that joint distribution I can just write down as A0, A1, B0, and B1. So that's what we're going to use. We're going to use this assumption to get restrictions on these probabilities. And what the Bell inequality will look like will be that a sum of a subset of those probabilities is less than some number, which I'll call beta. So what we're going to have to do is find out what that number beta is, and we're also going to have to figure out what subset of probabilities we're going to be interested in taking. And that subset is actually going to be dictated by looking at the quantum mechanical situation. So let's go ahead and do that next. Now we're going to go to the quantum mechanical method. Now what we need are 2 bases. We have 2 observables, and we'll just look at Alice for the moment. We have A0 and A1. And we're going to assume that Alice and Bob both have qubits. So we're in a two-dimensional Hilbert space. Now, A0 has two eigenstates. And what we're going to do is we're going to choose those eigenstates to be the computational basis 0 and 1. So A0 is going to correspond to the basis 0 and 1. And we're going to have that A0, 0 is equal to 0. And A0, 1 is equal to 1. Now for A1, we're going to need a second basis. And for the moment, we'll just call it V0 and V1, and without specifying exactly what it is. And we will have that A1 V0 equals 0, and A1 V1 equals V1. So that what that means is that I can choose A0 is simply going to be equal to 1, 1, and A1 is going to be equal to V1. That. Now, what we've got one basis, okay, computational basis. How do we get the other one? What we're going to do is we're going to choose a unitary operator. So that U squared is equal to the Pauli matrix sigma x. And if you remember what sigma x does, sigma x acting on 0 gives 1, and sigma x acting on 1 gives 0. It just flips the states. Now, making this assumption, we'll see why we want to do this in just a minute. Making this assumption, we also, if I square both sides, that u to the fourth equals sigma x squared is just the identity. Now for the other basis, what I'm going to do is I'm just going to start applying u to 0 and see what happens. So let's take u acting on 0, and then we're going to take u squared acting on 0, and we're going to take u cubed acting on 0. And actually, I should go back here. We're going to start with 0. So what does this do? Now, 0 is 0. U acting on 0, I'm going to call V0. So I'm going to take that to define my second basis. U squared acting on 0, well, that's just sigma x acting on 0. That's just going to be 1. And then u cubed acting on 0. I'm going to call that V1. And that is my the second element of my second basis. So my claim is that these two things form a basis. And clearly, 0 and 1 form an orthonormal basis. Now, what I need to do is I need to show that V0 and V1 are orthogonal, because I'm claiming they're an orthonormal basis. Clearly, this one is, because remember we found out that this was simply 1, and 1 is orthogonal to 0. So let's go ahead and show that these two things are orthogonal. So I'm going to take V1, V0 equals 0 U inverse cubed, because that's the V1, and then I have a U0, which is the V0. This is simply equal to, okay, one of the U inverses is canceled, so I'm going to get a 0 U inverse squared 0. This, in fact, if I move the U inverse over to the other side, that would be a sigma x acting on the 1. So that is simply going to be equal to 1, 0, which is in fact just 0. So that shows that those are an orthonormal basis. And let's just write down u explicitly here. So a choice of u. So remember, u squared is equal to sigma x. One way of making that happen is choosing plus x, and then I'm going to have plus I times minus x, and plus minus x is equal to 1 over square root of 2 times 0 plus minus 1. Those are eigenstates of sigma x. So the sigma x should just look like plus x with a minus sign here, minus x. So you see that if I square the u, that I'm going to get an I squared there. That will turn into the minus sign, and that will give me my sigma x. We have the variables already, and we also have that u to the fourth equals I. So just to mention, that means that u is a two-dimensional representation of the group Z4. Z4 is addition mod 4. Another way of writing it is that it is equal to some generator G to the J, where J equals 0, 1, 2, and 3. And of course, G to the fourth would be equal to the identity. And the mapping is simply that U to the J corresponds to G to the J. So U to the fourth is the identity, G to the fourth is the group identity. So U is in fact just a two-dimensional representation of the group Z4. And this can be used to build up bigger Bell inequalities than the ones that we're actually going to do. But we're going to stick with this simple one here just to show how the machinery works. And if you want to find out how to build bigger Bell inequalities, there will be some references provided at the end. Now, what we're going to do is, so this is just for Alice, but we also have to now include Bob. So Alice is in a two-dimensional Hilbert space, and Bob is in a two-dimensional Hilbert space. We put them together, we get a four-dimensional Hilbert space. Now what we're going to do is we're going to go to that four-dimensional Hilbert space, and so we're going to go to Alice-Bob space, which is four-dimensional. And instead of U taking various powers, we're going to go to U tensor U. And one for Alice and one for Bob. And we have that G to the J goes to U tensor U to the J. So U tensor U is a four-dimensional representation of Z4. And as I said, when we get this procedure can be adapted to bigger groups. The group Z4 is an abelian group. Everything commutes nicely. We can also take this to non-abelian groups. And then one of the references, it's done for the dihedral group D3. Now, the next thing we're going to do is we're going to create two things called orbits. This comes from the theory of something called group actions, which we're not going to get into because we really don't need it. What we're going to do is we're going to take U tensor U, and we're going to apply it to two different starting points. So the first starting point, I'm just going to take 0, 0. And if I just let J equal 0, 1, 2, and 3, what I get is I get a sequence of states 0, 0, V0, V0, 1, 1, V1, V1. And then I'm going to take a second one because these are the things that are going to tell us what the subset of probabilities is. So we'll discuss how that works in just a second. And it turns that would be a set of 4 probabilities. That's really not enough. I'm going to need 4 more. So I'm going to pick a different starting point, V0, 0, do the same thing, and this generates a second orbit. So again, I start out with V0, 0, and then applying U once, I get 1 V0. Applying it twice, I get V1, 1, and applying it 3 times, I get 0 V1. Now, so how do these things define probabilities? Well, suppose we're given a quantum state psi. It's a 2-qubit state. So suppose we want to know what is the probability that if I measure A0 and B0 in psi, that I get 0 for both of them. So in particular, we're going to be interested in A0 equals 0 and B0 equals 0. Remember, these are the probabilities that Alice and Bob can get at by doing measurements on their system. Well, this is simply equal to 0, 0, and psi squared. So you see that this particular probability is related to this particular state. So each of these states up here defines a particular probability of this kind. Let's do one more. So the probability that A1 equals 0 and B0 equals 0 is equal to A1 equals 0, that means V0, okay? And B0 equals 0 means 0. So that means that this is simply going to be given by V0, 0, psi squared. So each of the states in these 2 orbits defines a probability. Just like this for some state psi. Well, we've got 8 elements in the 2 orbits together, 4 in each. So that means that we have a total of 8 probabilities. And that's going to be the subset of probabilities that we talked about earlier. Remember, we said the Bell inequality is going to be some subset of probabilities that when you add them all up has to be less than something. And in our case, the probabilities are going to be the 8 probabilities that come from here. And then we're going to show that if it's a hidden variable theory, that they have to be less than something. And we're also going to show that if probability comes from quantum mechanics, it's going to be able to violate that bound. So now let's talk about adding up all the probabilities. How can I express that? So the sum of all the probabilities together is just going to be equal to psi A psi. So what is A? So A is going to be some operator. So A is going to be equal to the following thing. It's going to be the sum from j equals 0 to 3. And it's going to be U tensor U to the j. And then it's going to be my 2 orbits. So I'm going to have 0, 0, 0, 0, plus, and then the other one, V0, 0, V0, 0. And then I have to do the U's again. It's going to be U dagger tensor U dagger to the J. Now, what we want to find out is how big can that be? Because we want to make that as large as possible. The reason for doing that is, as we'll see in just a minute, that will guarantee that the violation of the Bell inequality is as large as possible. Now, how can we find that? Well, A is a Hermitian operator. The biggest it can be is the largest eigenvalue of A. So the answer So what is that? Well, I'll spare you the calculation. It's not bad. I mean, we're talking about a four-dimensional system here. It turns out that the largest eigenvalue is equal to 2 plus square root of 2. And just to write it down, the eigenstate, the corresponding eigenstate, is equal to, I'm going to call it phi max. And that is, in fact, equal to 1 over square root of 2 times plus x minus x plus e to the I pi over 4 times minus x plus x. So let's just see what we have here. For that state, phi max, the sum of the 8 probabilities is just going to be equal to that. And just to, as a kind of a side comment, when we calculate those probabilities, things the ones in our set, we find out that they're all the same. And so for phi max, each of the probabilities is just equal to an eighth of this thing. All right, so that's the quantum mechanical side. So the next thing we want to tackle is the classical side. So we know that there's a state for in which the quantum mechanical probabilities will add up to 2 plus square root of 2. Now let's assume the probabilities come from a local hidden variable theory and see how big that can get. Now let's do the classical probabilities. So we're going to get those probabilities from that joint distribution. So the classical probabilities, or hidden variable ones better, okay, come from our joint distribution, which remember look like PA0, A1, B0, and B1. So let's calculate one of them just as an example. So suppose we want to calculate PA0 equals 0 and PB0 equals 0. So what's that going to be? Well, it's going to be the sum over A1, B1 equals 0 to 1 of our joint distribution where A0 is 0, so that's a 0 in the first slot, and that's an A1 in the second slot, and B0 is also 0, so that's a 0 over here, and then I have B1. So it's just a sum of some of the elements of the joint probability distribution. So what we do is we express each of the 8 probabilities in this form, and then we add everything up. So what does the sum of the 8 probabilities look like? It's going to look like the following. It's going to look like sum A0, A1, sum B0, B1, where the sums are both from 0 to 1. And I'm going to have some number out here, say A0, A1, B0, B1, and then I'm going to have the joint probabilities. Now, the reason for these, so I'm taking 8 expressions like this for different probabilities and adding them up. So what that means is that some of the elements of the joint probability distribution are going to appear more than once. And that's what the C's are. So the C's are actually positive integers. So C A0, A1, B0, B1 is just the number of times that that particular combination of A0, A1, B0, B1 appears. So these are positive integers. Now, we want to find the maximum value of this sum. Now, the sum of all of these guys without the C's is simply equal to 1. And that means that what we do is we look for the biggest value of C here, and then we put all the probability into that value. Remember, we can choose this any way we want. So we find the biggest one of these, and then we just assign that thing a probability of 1. So that means that the maximum value of the sum is just going to be the biggest value of the C0, A1, A0, A1, B0, B1. So this is going to be less than or equal to the max over A0, A1, B0, B1 of C A0, A1, B0, B1. And we can actually find out what that is. So you have to do the calculation. You just take the probability, add them all up, find out what the C's are. It turns out that that is, in fact, in our case, is equal to 3. So that means that the Bell inequality is that the sum of our 8 probabilities has to be less than or equal to 3. And what we found from quantum mechanics is that we have a quantum state where the sum is equal to 2 plus square root of 2. And so the quantum state being phi max. And you can see, okay, square root of 2 is about 1.4. So the quantum mechanical result is about 3.4. That is definitely bigger than 3. So we have a violation, quantum violation. And just to be clear, this is in fact the Bell inequality. So the sum of, according to local hidden variables, that sum of those 8 probabilities has got to be less than or equal to 3. And what quantum mechanics tells us is that it in fact can be as big as 2 plus square root of 2. So we have a violation of the Bell inequality.